Hello everyone, my name is Fabrizio Nocera and I'm a postdoctoral research fellow at University College London. The title of my presentation today is Framework for the Resilience Assessment of Supply Chains. This work was done during my PhD at the University of Illinois in collaboration with Alessandro Contento and under the supervision of Professor Paolo Gardoni. Starting with some motivation, the well-being and economic prosperity of societies depend on critical infrastructure. Because infrastructure provides the continuous flow of essential resources and services that support societies. Critical infrastructure enables individuals to achieve valuable states and also perform necessary activities. However, past events have highlighted the vulnerability of infrastructure to disruptions caused by natural or anthropogenic hazards. While much research has been devoted to assessing the performance of individual infrastructure components, such as bridges, electric substations, and also water pipelines, and individual infrastructure such as transportation, power, and potable water infrastructure when facing a natural hazard, there has been limited efforts to link failures and disruptions in critical infrastructure to failures and disruptions in systems like businesses and also their supply chains. Supply chains involve multimodal transportation systems that span multiple countries for sourcing and supplying goods and services. And also, supply chains rely on well-established routes that comply with several economic constraints. However, natural hazard may affect the supply chain by making transportation segments unavailable, requiring alternative routes, and also limiting the performance of hubs. Now, I bring the hubs into the picture because in a supply chain, hubs play a major role in the movement of goods because they connect many sources with many destinations. And we can classify hubs into two main categories that are the distribution logistics hubs, like the warehouses, and transport logistics hubs, like ports or freight stations. The distribution logistics hubs are the facilities where the businesses hold their inventories and from which they receive the goods to sell, whereas the transport logistics hubs are complex systems where the transshipment of goods occur and they do not serve as storage facilities. So the key point here is that these two types of hubs are completely different from each other and have different roles in a supply chain. Now, the performance of hubs affect the restocking ability of businesses and their profit, because natural hazards may hamper the ability of transport logistics hub to provide the requested goods to the distribution logistics hubs. Similarly, the reduced inventories in the distribution logistics hubs would impede the restocking ability of the retailers that will then experience a loss of profit because of the lack of goods to sell to their customers. If we look at the literature, supply chain resilience has gained increasing attention in recent years. Past research has focused on several aspects of supply chain resilience, including its definitions, and also the analysis of the impact of disruptions on supply chains. Like infrastructure resilience, the resilience of supply chains encompasses the response and the recovery of the supply chain after the occurrence of disruptive events and its ability to resist and absorb disruptions. However, current literature lacks a mathematical formulation to model and quantify the resilience of supply chains subject to disruptions. There is a need for models that are able to capture the propagation of the disruptions across the supply chains, and it is desirable to develop a mathematical formulation that quantifies the resilience of supply chains while we can capture the supply chain structure as a whole and also all the resulting effects of the propagation of the impact on the performance of the businesses of interest. So in this work, we propose a mathematical formulation to model and quantify the impact of natural hazards on supply chains by modeling the dependency of supply chain operations on physical structures and infrastructure and their potential damage. And specifically, the focus here is on the direct effects of the hazard on transport logistics hubs and then the cascading effects on businesses. So we propose to represent supply chains using graph theory. So mathematically, a graph is written as a collection of nodes and links, and then networks are graphs in which the nodes and links have also additional attributes that go beyond the topological information. Then we propose to model supply chains as a collection of networks, where each network captures a specific feature or function of the supply chain, And in addition then, in the proposed formulation, some selected nodes, like for example the transport logistics hub, are modeled as nested networks with their own capacity, demand, and supply measures. The transport logistics hub is modeled as a collection of two networks. We have a structural network that describes the connectivity and physical damage to the components of the transport logistics hub, and then a flow network describing its functionality in terms of the transmission of goods. At a certain time t, then, the flow capacity can be written as I'm showing here, in which we are showing the dependency of the capacity on state variables, variables that define the efficiency of the transport logistics hub, and then capacity, demand, and supply of the structural network, meaning that the flow network depends on the integrity of the structural network. Similarly, the flow demand can be written as a function of the demand of the retailers on the logistic distribution hubs. And finally, the flow supply can be written as I'm showing here, in which basically the intuition behind is that there is no need for rerouting when the transport logistics hub can meet the demand. Instead, an optimization of the supply from the transport logistics hub to the distribution logistics hubs is needed when the transport logistics hub can only partially meet its demand. To visualize what I've just introduced, let us consider the flow capacity of a port just as an example of transport logistics hub. So in this case, state variables would include the length of the wharf, the type of cranes, and also the depth of the channel. And similarly, the variables defining the efficiency of the transport logistics hub may include the number of working hours and the number of working cranes. Similarly, if we consider the flow demand of a port, so imagine we have a network that is composed of a port serving two distribution logistics hubs, which in turn they serve three retailers. So the demands on the retailers are lumped together to estimate the demands on the distribution logistics hubs. And similarly, the demand on the distribution logistics hubs are lumped together to estimate the demand on the port. Finally, considering the flow supply of a port, the supply will correspond to the amount of material that satisfies the demand on the distribution logistics hub between two consecutive shipments. So if there are no perturbations, the supply will equal the demand. Otherwise, we need to solve an optimization problem with restricted capacity, and we'll see more in the next few slides. So the distribution logistics hubs retailer segment of the supply chain is also modeled as a collection of two networks. And so we have a definition of capacity, demand, and supply at the retailer level. And similarly, we also have a definition of capacity, demand, and supply at the distribution logistics hub level. Specifically, we estimate the supply by solving an optimization problem. We model the flow of goods from source to destination by solving the following optimization problem that maximizes the profit of the entire supply chain subject to the constraints that I'm showing here. The first constraint will tell us that the amount of goods that leave the distribution logistics hub is less than the sum of the amount of goods in the distribution logistics hub and the amount of goods that arrive from the transport logistics hub to the distribution logistics hub. The second constraint will tell us that the distribution logistics hub do not ship more than the requested goods to the retailers. And lastly, the last constraint will tell us that the amount of goods that leave the transportation logistics hub cannot be greater than its capacity, which again depends on the performance of structures and infrastructure. So this is the key point of this work, because the damage and disruption to structures and infrastructure would alter the flow capacity of the transport logistics hub. As a cascading effect, the changes in this capacity will result in changes in the supply. And so finally, the reduced values of the supply result in a reduction of the capacity and supply of the retailers. We show the proposed formulation considering the supply chain of a nationwide retailer. So the considered supply chain includes transport and distribution logistics hubs and also the individual retailers. More specifically, the supply chain considered in this example is a portion in the southeast of the United States. So we aggregate the retailers based on their geographic location and the distribution logistics hub that typically serve them under normal operations. And in case of a disruption, if the distribution logistics hub that typically serves the retailer cannot satisfy the demand, then distribution logistics hub from neighboring areas may serve the retailers as well. As a disrupting event, we consider Hurricane Vilma that occurred in 2005. The functionality of the transport logistics hub is predicted to be compromised because of the storm surge or the wind. And then in this example, we also consider the role of structures on the performance of the port. So we estimate the changes in the capacity of the transport logistics hub. So the wind speed records and the inundation map allows defining the period of closure. And then we use the fragility functions to estimate the damage to the cranes and the reducibility of the transport logistics hub to unload the goods from the vessels. We use the estimated time varying capacity to estimate the number of goods supplied to the retailers. We use the estimated then number of goods supplied to the retailers to quantify the loss of profit of the retailers, and we summarize the results in terms of loss exceedance probability curve. In the interest of reducing the impact of natural hazards on supply chains, these results can help the decision makers determine the acceptable level of losses with a certain probability and conclude if mitigation actions should be needed to reduce such an impact. To conclude, we propose a mathematical formulation to model and quantify the impact of natural hazards on transport logistics hubs and their cascading effects on distribution logistics hubs and retailers. The mathematical formulation captures the dependency of supply chain operations on physical infrastructure and their potential damage. We illustrated the mathematical formulation by quantifying the impact of a hurricane on the performance of a port and the resulting cascading effects on the performance of a portion of the supply chain of a nationwide retailer. The proposed mathematical formulation can help decision makers in identifying mitigation strategies to reduce the impact in terms of the cumulative loss of profit from the retailers at the business level. And with that, I thank you all for your attention.